Hi everybody, so until now we learned that if I have some voltage, it's gonna make some current, gonna go in my circle, and this current in the wire gonna produce magnetic field. But the interesting question evolved. Maybe we can produce magnetic field and then it's gonna give us some current, and then we're gonna have some volt. So a lot of scientists were working on this model to try to understand it, and they built a smart device, this device, which you have a battery here, here's a battery, this connected to a solenoid, here it is, and what the solenoid do? Produce magnetic fields. This is the lines of the magnetic fields, so it's look like. And on the other hand, the other side of the experiments, they put another solenoid. And they were expecting that if this magnetic field can present current, we're gonna see it here. We're gonna see some change. You have here error. This is a plus, this is minus. We're gonna see change, you're gonna see some voltage, you're gonna see something here. But when they did this experiment, nothing happened. Until somebody really smart came along, which is Faraday. And Faraday is so genius that I would put him with the three great physicists. Let's do it like this. Here is Einstein. Here is Newton. And the 18th century, actually, it's Faraday. And what Faraday noticed is that when I turn on the circuit, let's do it like this. When I turn on the circuit, boom, I see something. But then it goes back, okay? I see the error changing. And if I open the circuit, boom, I see the error changing and then go back. So Faraday understood that actually when I use changing magnetic field, then I have some current and voltage. And further on, we understand that it's not the magnetic field, it's actually the flux. So let's write Faraday equation. So Faraday equation states that you're gonna have some electromotive force, which is actually volts, the unit, volts, and they're gonna be the changing of the magnetic flux by time. And don't forget to put Lorentz, the minus. Here the minus is actually Lorentz law. Okay, so let's remind you what is the magnetic flux. So the magnetic flux, like was in a Gauss law, it's the same flux, but right now I can use an open surface, and it's choose some surface A, have B the magnetic field dot dA. And remember what this is equal to? It's equal to the integral on A, the area, B, the magnitude, dA, the magnitude, and cosines, the angle between them. So actually, when we use Faraday law, we actually need to look at three main actors. One of them is that the magnetic field. The magnetic field can change. If the magnetic field is changing by time, if this is a function of time, so I'm gonna have some derivative here, which is not zero, and then I'm gonna produce some voltage. And if the angle between them gonna change, I also gonna have some voltage. This is the idea behind motors. I changing the angles. And if I changing the area of my loop, of my Gauss's area, why I say Gauss? This is an area, some area, I don't know. It's an open area, okay? If I'm gonna increase this one, for example, a bigger surface, so also I can have a non-zero derivative. So this is the idea. Okay? So we're gonna do today two examples. One of them we're gonna change the area, and one of them we're gonna change the magnetic field, And in the lecture you saw how to do a problem with changing angle. So let's dive into it. So our question is looking like this. Go like this. So we have this nice triangle with a really long wire and a really long, I don't need this also, really long wire, really long wire, okay? And here I'm gonna put a bar. Here's a bar, a massive bar with the mass, right? Massive bar with a mass M. And here the wire, the resistance is negligible, but this wire is not negligible at all. The resistance can be defined by gamma. Let's put here gamma. And gamma is actually, the unit is omega per meter. So if you remember the resistance was rho L over A, right? So gamma is actually presenting this. Okay, so the A does not change, the material does not change, so we can talk at gamma, right, a lambda, and we can multiply it by the length. Okay, the angle here between the two bars is pi over 3, and in all my wall there is a magnetic field everywhere, outside of the triangle and of course inside the triangle. Okay, and when I put this triangle, okay, here it is, of course you have some force because of the gravity, so this one is going down. Okay, so this is the problem, this is the given data, and I didn't say it, but B is constant. B is constant. And my question to you is, what is the area? The area of the triangle, this area. What is this area? Let's call it A. A equal to, so this is a triangle, and remember the triangle is the height multiplied by the base, okay, and divided by 2. So the height, so this height, let's call it y. We did here a y-axis. So this is y, and it's a function of t. Why? Because this bar is falling and this triangle getting bigger and bigger, higher and higher, right? So, and we also have the base. The base is gonna be this distance. Let's from base, let's call it b. It's small b because we have the magnetic b, okay, and this is divided by 2. Perfect. So y is y, and b we can find out b from, you see that I can divide this to pi over 6, this triangle, right? And I know this angle, and I want to know this angle, so I'm going to use tangents, right? And I can get this, the tangents, because I know the angle. So this b is actually at the end gonna be 2y t over t to the third, root of t over 3, y, and all of this over 2. The 2 can go, and I have y squared, so a is actually equal to y squared, which is a function of t, and 3. So we found the area, and we see that the area is actually changing by time. Okay, so the question to you right now is actually why there will be some current inside this triangle. The current is gonna go here, here, then go take here, go up. There's gonna be some current inside this loop. If you're gonna put here some lamp or a fan, or you want to plug your computer in and charge it, you can do it. Why it's gonna happen? So the answer is easy. You see that A is getting with time bigger and bigger and bigger. You see it? If A change, the flux must change. The flux also increasing, right? If the flux changing in time, we're gonna have some EMF, right? Some voltage. And if you have some voltage, you're gonna have some current. Okay? So this is the reason why you're gonna have current inside this loop. Okay? Perfect. Let's move on to the next question. Okay, so the next question is, what is actually the flux? Let's find the flux. Okay, let's do it. So, let me clean this one and this one. Okay, so what is the flux? So remember the definition of the flux. The flux is phi b, like friends, you know, phi b, equal to the integral on the area b dot dA. Okay, and I'm gonna choose dA to be in the direction of the magnetic field, so I can get rid of the vectors, right? If it's pointing in this way and the magnetic field also pointing this way, I'm done, everything is okay. So I did this, and I know that b is constant, remember? So I can take b outside, and what I left with is b integral of a dA. And what is in this integral? If you're gonna sum all the small dA's, right? So eventually you're gonna end up with what? With a. So phi b is equal to at, which is this term, yt squared 3 multiplied by b 0. So we found phi b, and as we said before, the flux, the magnetic flux, is changing by time. So perfect, we can see it, we can see the relation. Wonderful. So right now I want us to calculate what is actually the voltage that's being produced inside this loop, inside this frame, right? So what it's equal to? So we know, according to Faraday's law, that the voltage is equal to minus the derivative of the flux. Okay, so we know the flux, we can just derivative it. So what is the derivative? Let's do here like this. So it's getting 2y multiplied by y dot y. It's the internal derivative, right, of y, b 0 and square 3. So this is the derivative. So this is the answer here. I'm just gonna put the minus sign. Minus 2y y dot b 0 over 3. See, it's okay. Yes, that's it. Right? And this is also a function of time, because this is a function of time and this is a function of time, right? Good. Okay, let's move on. So the next question is, what is the resistance of this bar? Okay, so the resistance of the bar, we just talked about it at the beginning, talked about it before. So the resistance of the bar is given as R equal to, we said that rho L A, right? But it's not the same A, by the way. This is A, which A? This one, that the current need to go through. This is not the same A, so let's do A star. Okay, it's not the same one. It's the A of the resistor. Okay, and this is given, this is called lambda. So lambda multiplied by L. What is L? L is the length which the current going through. So we call this the base. Remember, we give it a name already. So it's actually B, and B changing in time. Why? Because in this position, look how big B is. And in this position, is even getting bigger, okay? So B equal to, this one is, we calculated, is 2y over square root of 3. So this is R. We found R. And the next question I want to ask you is, what is actually the current that goes inside this loop? It's pretty easy, remember from the previous tutorials? So we talked about that we have Ohm's law. And Ohm's law, Beer law, is applied also here. So the voltage equal to IR. So if I want to find I just need to take epsilon divided by R. This is changing in time, this is changing in time, so probably this is changing in time. Perfect. So we just need to divide them, these two. So the current, let's write it here, is this term divided by this term, which is give you the result of minus y dot. The minus is coming from here, the y and y go away, the 2 and 2 go away, y and y go away, the third go away, everything go away, and we're left with y dot over lambda. So this is the current that we have in the loop. Wonderful. What are the forces that apply on this bar? Okay, we can read of this. What are the forces that apply on this bar? So the forces that apply on this bar, first of all, there's gravity. Perfect, right. But is there another force? Okay, think about the previous tutorials. So if we have a beam, some conductor with current inside, and we have a magnetic field, we actually have Lorentz force. So we actually have Lorentz force, F equal I integral B dot dl. Okay, from the beginning to the end of this bar. Okay, so B and dl are perpendicular to each other, so I can take B also outside. It's a constant, I B0 L. And a method for me to remember this equation by memory, you know, by heart, is I think about it. You know this device, this loudspeaker of JBL, right? So I think about it as JBL. I know the J is the current density, so it's kind of a current, right? So IBL, JBL, that's for me the method to remember it, but it's up to you. I always believe that to remember equation by heart is making you stronger the exam, because when you go through the equation, you're actually coming up with the ideas because you remember the equation or you understand really fast what's going on. It's another level of profession. I recommend to you to remember the basic equations. Remember them. They are good to remember, okay? So, we actually know the current, so we know F. F is minus y dot B lambda L, right? So this is F, this is the force that we have. And what other force that we have? Yes, we have, this is Lorentz force, and we have also the gravitation force, which is mg. So if I would actually want to write the equation of the force applied on this bar, I can actually take, where is it? Here it is. I can just simply write, that total of the forces, right, equal to the mass multiplied by the acceleration. The acceleration can be presented by y dot dot. mg is in the positive direction because I declared this is my positive sign of y-axis. So actually it just need to be the summation of both of them. So it's, this term is actually mg. Let's write everything. Okay, let's write it how it should be. Okay, so here I have, this one is mg minus y dot b l lambda equal to my dot dot. Okay, so if you want to ask which force is gonna take over, maybe they're gonna balance each other, so it's up to you. You can say that y dot dot is equal to 0, and then it means that they are balanced, they're equal to each other, and this moves in a constant velocity. We can say that this is negative, this is positive, and this is positive. So if this term is negative, it means that this term is actually taking over. If it's positive, this term is actually taking over. Okay, so the sign of the acceleration. So this could be another question, but we're not gonna deal with that. This is physics 1 and we're here for physics 2. So I want to ask you a question. What is the direction which the current gonna go inside this loop? You're gonna go clockwise or other clockwise? Okay, so the answer for that question is simply by Lenz's law. Remember that I told you that, here it is, that the voltage that I'm gonna have, the voltage is actually minus dpb dt. And what is this minus? This is Lorentz law. Okay, Lorentz law declare that the current that the voltage that's gonna apply here gonna resist its formation. What do I mean by that? I want you to think about physics 1. If I have some, I don't know, table or a chair or something that I want to push, so I'm gonna have friction. Okay, friction is the analogy here. Okay, I'm gonna have some friction. What is this friction? It's some energy that resists me moving the box. Okay, and the friction always gonna be on the negative side, right? So if you're gonna push it in the positive direction, the friction gonna be against me. If I'm gonna push it to the other direction, the friction gonna be at the positive direction, right? So that's the idea. So why it's happening is actually happening for a conservation of energy. Think about it. If you push something and the friction would help you, so you're gonna push it, or you're gonna accelerate it even more, so more energy. And then you're gonna have more friction, and you're still pushing it, it's gonna get more energy and more energy, more energy, because the friction would not try to stop you. So the same idea going here. So if you increase the area of this term, so this kind of energy would like to resist you, they would like to fight you, okay, to stop the change, okay? So for example, and how it's gonna do it? It's gonna do it with the current. Okay, current produce magnetic fields, and we want to stop the flux from growing. So what's happened to me? Because A change, this is A after a few seconds, you see that I'm catching more and more magnetic fields, right? The area is increasing. Here I have way more magnetic fields, right? The integral is bigger, A becoming bigger of the flux. Here I write the flux again. The flux, only this term, is the integral of B dA. Okay? A. So A actually increasing. Okay, I'm gonna sum more dA, more multiplication by B. So the current gonna be like this, that they're gonna stop the flux. It would not succeed, maybe it will, maybe it not. We talked about it in the equation before, but you try to stop. How it can stop it? It can fight the magnetic field. For here an example, I have magnetic fields that go inside the board. So this one will try to produce, So this one will try to produce a magnetic field that will try to what? Weaken the flux. So the one that's going to weaken the flux is actually one that's going here and going outside here, right? So I need to find current that will actually produce magnetic fields that will try to fight this magnetic field in order to make the flux smaller. So this one is actually going to be with the right hand rule in this direction, here in this direction, you can see it clearly, and here in this direction it's going out. So it's actually going the other way of the clock, right? It's going in this direction, the current. Okay, so this is the idea. And what I want you to emphasize here is the idea is that it will not try to take the flux down or taking the flux up. It will try to do the opposite, which means in our case the flux is actually getting bigger. So right now we will try to fight the flux. That's what the current will try to do. It will try to stop the flux from growing, for the energy to accumulate to infinity. Okay, that's what's going to happen. Okay? In other cases, when the flux is actually dying out, okay, this voltage will try to help the flux, and that's what we're going to see in the next question. Okay? So let's move to the next question. Okay guys, so the next question is about Amazon, okay? Why about Amazon? Because Amazon have a lot of drones, okay? And these drones actually suppose, I don't know how to draw a drone, I don't know, like this, maybe like this something. And the drone should take your boxes, okay, to your location in the city. So this is the idea, okay? So these drones, Amazon drones, will take boxes and deliveries to your home. But the problem is that inside the city you have a lot of obstacles to overcome, right? For example, you can have some electricity wires. So how these drones can sense the electricity wire, okay, of the electricity wire, and get away of it and not stuckle into it, okay? So for that we have the next question. So let me try to draw it in a different manner. Okay, so here it is. So we have here a wire, electricity wire, okay? And the electricity wire, what is doing in the space? It's producing magnetic fields, right? So the right hand rule, okay? So the magnetic field is actually, if the current is going like this, so here we're gonna have, in this side of the board, I'm gonna have the magnetic field pumping out of my board, right? That's what's gonna happen. And in the other side, it's gonna flip around because it's in a circle around this wire. Okay? And here I have some drone, okay, that passed away this wire, okay? So here's the drone. Here's the drones. And the drone have some electric loop inside here. This is our sensor. It's not all the drone, it's the part of the drone. And the drone moving in this velocity. So the drone was actually alert that it's gonna go closer to some wire and move on, okay? And let's do an axis, okay? So this is gonna be our y-axis, okay? And this is gonna be our x-axis. Okay, this is the origin. Let's do it even here. X-axis. And the magnitude of this loop is actually here. Here is the location where we started, y0. Okay, this is yt, our location, general location. And this size is a, and this size is b. So this is b, and this is yt plus a. Okay, this place. Okay, and this thing is moving with the constant velocity. It's important to say constant velocity. And okay, so this is actually the question. So the first thing I want to ask you is what is the location of this drone as a function of time? Okay, so what is the location of the drone as a function of time? This should be easy from physics 1. So the location of the drone at the beginning, it was in some location, y0, and then it moved in some velocity v, right? So it moves some velocity v, constant velocity, and time t. So this is the first question. So this is how the drone moving in space, okay, in our universe. Okay, perfect. And the second question is, what is the flux? What is the flux that go through the drone, through this loop of the drone? Okay, so let's write what is the definition of flux. Definition of flux is going around some area, calculate b multiplied by dA, and again I'm going to choose dA to be in the same direction of the magnetic field, so I can get rid, right, you see I have these angles, right, so I can get rid of the dot and the vectors. It's not vectors anymore because they are perpendicular to each other. The magnetic field right now is not constant. Remember, the magnetic field is actually changing by time because I'm going away from this wire. Remember what is the magnetic field of a wire? Let's write it down. So the magnetic field of a wire, if I do use Ampere's law around the wire, I know that the loop will be constant from some distance. Okay, let's call some distance. So mu 0 I equal to b going outside, 2 pi r from the integral. We did it in the previous tutorial, so I can divide by 2 pi r. So b is actually changing by mu 0 I, 2 pi, and instead of r I'm going to put y, because this is the distance, right, that they're talking about. For example, if I want to calculate the magnetic field of this dA, this is dy, and this is dx, so the magnetic field here is actually some y, some value y. Okay? Perfect. So this is the flux. Okay? And sorry, this is not the flux, this is the magnetic field. So we can write right now this term. So we are running on two variables because dA is consist of dx and dy. So we can write here dx and dy, and we know that the magnetic field is mu 0 I divided by 2 pi y, this distance, and we know that y is actually, let's do y star, okay, specific for the integral. So we know that that x is actually moving from 0, right, from 0 to b, and y actually moving from yt, the different location in time, till the last location, which is yt plus a, right? Yes, that's exactly what's in it. Okay, so that's the integral we need to solve, and it's not that complicated integral. I'm gonna clean this one out. It's hurting me to do that. Maybe we're gonna need it later. Okay, so remember this. I'm gonna give you an analogy for that, but I need the board. Okay, so let's solve this integral. So I can take all the constants outside. Okay, so the flux equal, let me write with the blue, it's easier to see. So the flux is equal to, take constant outside, mu 0, 2 pi, right? I also constant, and I can do the integral on b, right? There's nothing here that stopped me. So this is b, and when I do the integral, is integral of 1 over y. You see it? So it's ln. So this is actually ln. The integral is ln of y star, and y star can be what? Can be y yt and yt plus a, right? So I don't know if you remember it, but if I have this one is ln yt plus a minus ln yt, and according to the Lorentz law, I can actually, logarithmic law, I can actually change this minus to divide them instead of subtract them. So 2 pi b, as it's easier for me to see. You don't have to, but I love it more concise. Okay, so this is the term from the flux, and this one is changing by time. You can see this dependency. Perfect. Okay, how it changes by time? We know this, that yt is actually moving as this. It's actually ln of y0, where I started, plus v2 plus a, and here downstairs I have also y0 plus vt. Okay, perfect. So that's the term that I have there. Okay, and now we're gonna calculate what is the actually voltage that apply from our loop. Okay, so let's think about it. As this is the drones, okay? Here I have some wire and the drone is moving. So some of the magnetic field from the wire actually coming to this loop, and this is the area. Okay, that's right. This is actually A, right? This is small a, this is from here to here. This is B, right? And this is a small dA, right? You see? This is, that's it. And right now when I'm here, and this is the wire that's going in this direction, right? So let's do it. The current coming to my side, okay? You electrify me, okay? So this is direction. So the magnetic field is actually going through this wire, but this wire going away. So the flux is actually getting weaker and weaker because the magnetic field is becoming weaker. Okay, so the area stay the same, the angles stay the same, but the magnetic field is dying out. Okay, so let's calculate what is the voltage that produced here, you see in the wood of this board. The wood, what is actually the current that go inside of it. Okay, so we have this term, and the only thing we need to do, let's clean this one. 2 pi and u0 IB over 2 pi. Okay, so this is phi b. We found phi b from France. Okay, phi b from France. Okay, to calculate the voltage, what we need to do is use Faraday law. This is the idea of this tutorial. So this is minus, right? The derivative of the flux. Okay, and if I want to the derivative of ln, don't know if you remember, but ln derivative, right? If I have here fx, okay, so if I want a derivative this one, so it's gonna be f derivative divided by f normal. Okay, so that is the solution. So we can just put downstairs this one, this monster, right? This go outside of the integral, and I want you to notice that this current is not the current of the wire of the loop that we have. This is the current of the wire. This is the one that produced the magnetic field, right? So this is not changing in time; it's constant. Okay, from the company. And here I have this term downstairs. We have this as usual, right? So I'm gonna save time for you. Okay, I'm gonna just give you the answer of this. It's really easy. So we're gonna calculate it. We're gonna use this term to simplify it, and we're gonna get that the voltage, change it by time, of course, is actually equal to B mu0 I V go outside 2 pi, and I don't have here any space. Okay, so let's clean everything. It's correct what I said, but I just wanna write it with enough space so I can talk about the equation. So B mu0 I, the wire V of my drone, 2 pi, and here I put inside 1 over Vt plus y0 plus A minus 1 over Vt plus y0. I want to remind you that I should have here the 0 at the beginning, but I put the 0 inside here. So the minus was included. I didn't forget it. And my question to you is, what is actually the resistance? Sorry, not the resistance. The current, not this one. The current inside the loop, that around the loop. Okay, around the here in the wood. Okay. So what is this current? It's actually taking Ohm's law, which means to take the voltage and divide it by the resistance of the loop, which is given. And then you can find this term. It's a long term. We don't need to do it. And right now I want to ask you, what is the direction? Okay, is this, just use this term. What is the direction of the current? So if we have here the wire, and we are going far away, right? And here I have some magnetic field, but this magnetic field is actually dying out. Okay, the flux is getting weaker. Here's the flux, and it's said, okay, the flux is actually getting weaker. So what Lorentz law we try to do? Lorentz law we try to help the flux not to die. It doesn't like changes. So we try to produce also magnetic fields that go inside the loop, right? So what is the direction? So this direction. So it's going from here to here to here. So with the clock, see it? Direction is like this. This is the direction of the loop. Okay? And let's play with the flux a little bit. So I'm gonna see how you react to the flux. So another question. The other question is going like this. So we have here, we have three different scenarios. We have the drone over here symmetrically. This is the wire. We have the drone over here, and we have the drone over here, and we have the drone. It's in the same size. Drone over here, and drone over here, far away from the wire. So this is the wire, and the wire produces magnetic field in which direction? Let's use the purple. So if the current is going like this, right? So this is the direction of the current. So we have here axis, big axis, right? Close to the wire. There are big axis close to the wire. And we have some big dots close to the wire, right? And here I have, it's not what I meant to, sorry, didn't throw this right. Okay, sorry about that. I want to do it symmetric. So this one, this one, and this one. Perfect. So here I have big dots, right? Big dots. And here I have big axis. I'm closing to the wire, but I also have a big dots, right? And far away, right? I have a smaller axis and smaller dots. The same thing apply here. Smaller axis, and right now even smaller axis. You barely can see them. What's going on here? Here I have axis, right? Yeah, axis. Sorry, want to do. What's happened to me? Okay, sorry about that. This is the last time, promise to you. Okay, so this is actually here. Just three phases. Here I have the big axis. You have the small axis, the tiny axis, and the tiny axis. You can barely see them, but it's X. Okay. So my question to you, finally, okay, my question to you is, what is the smallest flux here, and what is the biggest flux of the magnetic field? Okay. So sorry about the entertainment that you have, but okay. So here, what I can see that the magnetic field in this direction actually cancel with this magnetic field. Okay, what is the flux? The flux is phi b, right? Integral b dA. So when I'm gonna sum this one, they're gonna cancel out with this line, okay? And the line here cancel with this line here, okay? Because it's symmetric around the wire, okay? So the flux here, phi b1, is actually equal to 0, okay? Let's see what's going on in other time. In this time, this one cancel with this one, you see it? But I still have this, okay, which contribute to the integral. The integral is not gonna be 0 here, okay? Here they're gonna sum this one and this one and this one and this one, and I'm gonna sum minus. So they're gonna cancel up, but this one gonna sum up to something. So actually I can say that phi b2 is bigger than phi b1, okay? Which this one is 0. We talked about it. What's going on here? Here everybody contributes. Everybody in the same direction. The magnetic field in the same direction. So this is the biggest, okay? And the sign of the flux is depending in which direction you decide to put dA, okay? So dA actually determines the sign, okay, of the flux, but in magnitude, that's what's gonna happen. So magnitude. In any case, whatever direction you choose. So that's it. We finished this tutorial. In the lecture, you should see changing in angle, which is very important. And always remember that we have 3 players. All these questions are really easy. They are always the same. Maybe it's always the same, truly. Or somebody gonna change the magnetic field, and this is gonna change the flux, or somebody gonna change theta, the angle between our circuit and the magnetic field that been produced. or it's gonna change the area, okay, if I have a big integral or small integral. So this type of thing they can play with you. Maybe you can do another tricks with actually, you know, to add something from the previous tutorials. I don't know, something about the resistance like we had before, you saw it, and stuff like that, or maybe forces from physics 1. But the general idea of Faraday is just understand what's actually building the flux, which is the angle, the magnetic field, and the area. Okay, this is the true the three parameters that you need to look at and be careful about them. That's it, guys. Good luck with the homework. I'm gonna see you next week.